Right. Math466, lecture 28, trying to figure out how to deal with matrices and calculate eigenvalues. We've seen we do not want to go the route of characteristic of the determinant and trying to do that. It's not going to work. So I have printed out my notes from the book, so if I start getting lost, I will glance down and look at them. There's a lot of technical calculations here. And in some sense, you almost want to just look at the big picture as to how we go about understanding this. So up until about 10 years ago, we could only prove results about spacings between eigenvalues for eigenvalues drawn from what's called the Gaussian orthogonal ensemble. And this was the distribution where things were tractable computationally. And so it's a little bit different than the ensembles we've looked at. We're no longer going to choose all the entries independent, identically distributed. Almost. The main diagonal will be a little bit different. Now, the set of matrices is called the Gaussian orthogonal ensemble. Any guess for what the density will be? Gaussian. So while it's somewhat specific and very particular and specialized, it turns out this is the most important of all cases to study. And the reason it's the most important case to study is in physics, we believe that the laws of physics should be unchanged if I rotate the coordinate axes. The universe should not care which way I orient my fingers. So what I would want is I would want the probability of QA Q transpose to be the same as the probability of A. So QA Q transpose is just looking at A in a slightly different coordinate system. All I really care about are the eigenvalues. So the probability of this on this side is just going to be the probability of A11, probability of A12, probability of A22, and then it's going, yeah, we'll leave it like that. So I'm having some issues as to exactly where I should put this today, so let's try this. Okay. So we have the calculation on the right-hand side is very easy. The left-hand side is going to be much more involved and it's going to depend on Q. And so the idea is to do an infinitesimal rotation. And we'll rotate by basically epsilon. And then we'll take the limit as epsilon goes to 0. And then we want the order epsilon term to vanish so that these are the same in the limit. So the question is, how do we want to rotate? And this is why I want to look at my notes, because physicists and mathematicians have two slightly different notations. So Q of epsilon will be cosine epsilon minus sine of epsilon. Yes, I'm doing it the right way. Sine of epsilon, cosine of epsilon. So depending on how you want to do it, are you rotating the vector, are you rotating the coordinate axes? People put the negative sign in different places. Doesn't really matter. Well, if epsilon is extremely small, what does cosine of epsilon look like? 1. It looks like 1. So this is equal to 1 plus an error of size epsilon squared. All right, how about the next one? So let's try moving this significantly further back and seeing if that helps. So what about the second?
Do you get the epsilon squared from the Taylor expansion?
From the Taylor expansion, exactly. So this will be 1 plus epsilon squared. What about minus sine epsilon? What would that be?
0 plus square epsilon.
So it'll be minus epsilon.
Yeah.
And what's the error?
Oh, epsilon to the third.
It is order epsilon to the third. Because I've already got sizes of order epsilon squared, I'm going to just write order epsilon squared.
Sure.
Then down below, just by symmetry, it'll be epsilon plus order epsilon squared, and it'll be 1 plus order epsilon squared. Okay? So now what we want to do is we want to calculate Q epsilon A Q epsilon transpose. And this is where I will strongly encourage you to vote. Don't have Professor Miller do these calculations. Have Professor Miller look at his notes. Thank you. Good vote. Okay? There's really nothing enlightening or illuminating about doing this calculation. This is just matrix multiplication.
Sure.
And so when we go out, we will get the following. It'll be A11 minus 2 epsilon A12 plus order epsilon squared. A12 minus epsilon A22 minus A11 plus order epsilon squared. Same, because my matrix is real symmetric. And then the bottom will be A22 plus 2 epsilon A12 plus order epsilon squared. And so while we're really doing stuff right now for 2 by 2 matrices, the idea is that this similar type of argument should apply in general. And I can do basically a bunch of small rotations in different directions. OK, now I want to calculate what's the probability of this matrix. So it'll be the probability of this entry times the probability of this entry times the probability of this entry. OK, so we now want to calculate the probability of QA Q transpose. And it's going to be P. Oh, I think, yes, sorry. I'm not assuming all the densities are the same, so I have to put subscripts here. Right? In fact, we'll see later that the main diagonal is slightly different than the other, so I should really have a subscript here at this moment. All right, so it's going to be P11 of the first entry, or we'll say of the 1,1 entry, times P12 of the 1,2 entry times P22 of the 2,2 entry. So I now have these three things to evaluate. And you can really see there's no desire to write it out. Let's try to estimate what they should be. I only care about really the epsilon term. Anything of size epsilon squared and higher, I'm going to just consider this my error. So let's look at the first one. So we have P11 of A11 minus 2 epsilon A12 plus order epsilon squared. What should this be close to? The probability of A11. It should be close to the probability of A11 when epsilon is small. Well, good. It actually is. I've got an epsilon and an epsilon squared, so when epsilon is really, really small. OK, so how should I figure out what the error is? Or how would I approximate this? So I want to evaluate P11 at this point. What theorem can I use to evaluate the probability at this point? So let me. So what if I want to do f of x plus h is f of x how would you approximate this?
Take the limit of h goes to 0.
Well,
F of f prime.
Plus f prime at the point x times the distance.
Yeah, that's right.
And then you would have your next term plus an error term that would depend on, say, f double prime.
Yeah.
So I'll put maybe like an f double prime down here of size h squared. So this is like a beginning, this is like a two-term Taylor series expansion. If I wanted to use the mean value theorem, I would have to evaluate this not at x prime, but at some intermediate point. But this is almost the mean value theorem. F of x plus h minus f of x is the derivative at x times h. Not quite right. It's the derivative at some point close by. If I want to actually have the derivative at the point x, then I have to have an error term coming from the second derivative. All right, so I'll assume my function's at least twice differentiable. Not a big deal. And if you look at this, what's nice about this is these points will not have any epsilon in it. I'm evaluating the probability and its derivative at the point A11. The epsilons are coming in over there linearly. So what would I get? I would get P of A11. And now what's my error? I'll have plus P11 prime at A11 times how far I've moved, which is negative 2 epsilon, plus order epsilon squared. And if you want, I actually have some of the epsilon squared in here as well. I've got some epsilon squared coming from the fact that I should really have a second term in my Taylor expansion. And I have some epsilon squared. I shouldn't be evaluating this at negative 2 epsilon. I should be evaluating negative 2 epsilon A12 plus order epsilon squared. Oh, so actually I should have a A12 as well. Minus 2 epsilon A12. So just rewriting it, it'll be P11 of A11 minus 2 epsilon A12 P11 prime A11 plus order epsilon squared. And I will check. I don't think I've made a mistake up until this point. Good. Okay. Any questions as to how we do this? Yes?
Is P11 like the probability that A11 has that value?
So A11 is drawn from a probability distribution with density P11. A12 is drawn from a probability distribution where P12 is the density, and A22 is drawn from a probability distribution where P22 is the density. So if you want, the probability that, say, A11 is in an interval alpha beta would just be the integral from alpha to beta of P of, say, P11 of T dt.
And this is a symmetric matrix, 2 by 2 symmetric.
It's a 2 by 2 symmetric matrix. So the probability of the matrix is going to be the product of the probabilities. And so I don't have to worry about the lower triagonal piece. Okay, now we just do the same thing for P12. And so P12 of my new point, if you want, we can call it maybe A12 epsilon. It will be P12 of A12 plus blah. And similarly, P22 of A22 epsilon will be P22 of A22 plus blah. Right? So we just Taylor expand all three places. And now we have to just multiply them all together. So, again, I'm not going to go through all the algebra and writing everything down. All right, so we'll get rid of this. And so now we have, somewhat long involved expressions. And so I'm going to skip ahead with some of the algebra, and I'm going to just look at the probability of A minus the probability of QA Q transpose. And then just to make life a little bit easier, I'm going to divide by P11 of A11, P12 of A12, P22 of A22. So I just want to convince you at this point that there is no thinking going on. Right? I've already got the Taylor expansions for all the three probabilities. I multiply them all out here. I subtract that from here. I divide by this. And the reason I almost want to divide by this is that's what the main term should be. And this will give you some sense of the right size. So when we go through and we do the algebra, we get the following. We get 2A12 over P11 A11 P11 prime at A11 plus A22 minus A11 over P12 of A12 P12 prime of A12. And then the last is minus 2A12 over P22 A22 P22 prime of A22 times epsilon plus order epsilon squared. Okay. So this is just algebra. So do we all agree that just getting to this stage is just doing some algebra? Now, in order for these two probabilities to be the same, the coefficient of epsilon must be 0. If it's not, then I've got a change in probability. So I need the coefficient of epsilon to be 0. Okay? So this bracketed expression has to be 0. Okay? Otherwise, if I make a small rotation, if this bracketed quantity went 0, the order epsilon squared piece can't be enough to cancel this if epsilon is sufficiently small. So this is the main idea. Because this is supposed to be invariant, it's supposed to be unchanged if I do a small infinitesimal rotation, if this wasn't 0, if I take epsilon sufficiently small, the epsilon squared piece can't cancel this and the probabilities would differ. Because the probabilities are the same, the only way that can happen is the epsilon term must be 0. And so now I have this wonderful differential equation to solve with 3 variables. Right?
So, question?
Yes.
So, but they should be 0 even if you rotate. But they should be like the difference should be 0 no
Right.
matter what degree you rotate, right?
Correct.
And so, but epsilon helps us prove because of the orders term.
Right, so if epsilon is really small, the epsilon squared piece can't cancel out this piece. If epsilon were large,
Right.
then this could cancel that out. And then my expansions here would be bad expansions. But because epsilon is extremely small, the only way this can be 0 is if the bracketed quantity, say the bracketed quantity is 1 billionth. Well, take epsilon to be so small that no matter how large this coefficient, even if this coefficient here is a googolplex, epsilon over 1 billion will be larger than a googolplex times epsilon squared once epsilon is really, really small. And so this is the key insight, is the only way we can have this hold when epsilon is really small is if the bracketed quantity is 0. And so this is going to give us a differential equation for the p's. Now the problem is, it is not a nice differential equation initially. How many of you have taken a class on differential equations? Excellent. Okay, well, I'm not asking whether or not you remember things. I'm just at least asking if you've taken it. There's a lot of people who wish more students took differential equations. A lot of times you get special functions and you want to solve things. So the question is, what is the best way to break things up? And so after writing some of the algebra around, we can rewrite this in the following way. 1 over A12, P12 of A12. Then I'll write it as dP12 dA12 equals 1 over, negative 2 over A22 minus A11, 1 over P11 A11 dP11 dA11 minus 1 over P22 A22 dP22 dA22. Okay. So we got this by saying this has to equal 0. We've got here the P12 prime. That's this piece over here. And now, why are we doing things like this? Well, notice that, yes?
Why are we calculating this, particularly the difference between the probability of A having all these values versus like rotated A?
We're calculating what's the probability we observe the matrix A and what's the probability we observe the matrix QAQ transpose. So QAQ transpose and A are different matrices, but they correspond to the same transformation just in a different basis. So one way to look at what QAQ transpose does is it rotates the basis. by a very small amount.
I thought we assumed that the probability of Q transpose has to be the same as A because...
Right. So what we're saying is we want to choose our probability densities so that this holds.
Okay.
So right now we don't know what densities make this hold. Maybe every density makes it hold, or maybe this is going to be some kind of restriction. And so the reason we want this condition is physically it's a reasonable condition. Physics should not depend on how I went to my fingers. Do people know Einstein's famous quote about God and dice? God does not play dice with the universe. Einstein had serious reservations about quantum mechanics.
Have you heard the quote on prime numbers?
Oh, no, I was going to say, I thought you were going to do Neil Bohr's response.
Oh.
Stop telling God what to do. What's the primes?
It's God doesn't play dice with the universe, but there's definitely something weird going on.
We're going with the primes. Yeah, who's that by?
I forgot.
I've definitely read that paper. And so this is a reasonable physical principle to start with, is that we do not want physics to depend on the coordinate system. And really, these are the same transformations, just written down in a different coordinate system. In some sense, this goes back to when we did our linear algebra review and we counted how many degrees of freedom do we have and where are the degrees of freedom. There were the eigenvalues and there...
Erdish.
It was Erdish?
Yeah.
Okay.
Of course.
Yeah.
Of course.
No, my favorite Erdish quote is, this is involving Ramsey numbers. If an alien fleet were to show up outside Earth and demand we calculate R55 in a year or they'll destroy us, we do so. If they want R66, we fight.
Yep.
That was...
The quote is, we would have no choice but to launch a preemptive attack. Yeah, this is...
Yes, normally you don't get to talk about alien fleets in mathematics. But so if we assume this, what are the consequences? What do we have to choose for our probabilities? It would be wonderful if they were completely free. But it would also be wonderful if they're not. Because right now when we're doing random matrix theory, I'm choosing a matrix by choosing the entries at random. Well, what distribution am I using? Why am I choosing this distribution versus that distribution? There's some arbitrariness. How many of you have seen classical compact groups? So, have you seen unitary matrices? These show up if you want to diagonalize a complex Hermitian matrices or orthogonal matrices. So if you look at orthogonal matrices, they form a compact group. The product of two orthogonal matrices is orthogonal. And the inverse of an orthogonal is its transpose, which is also orthogonal. They are associative. So all the properties you want from a group, there's an identity, all the properties you want from a group hold. And you can define a probability measure on the space of orthogonal matrices. And it's a very natural measure. And so what you can say is, I'm going to choose orthogonal matrices from this natural probability distribution. It's called the Haar measure. And what's nice about this is now there's a natural sense in which we choose our elements. Over here, we're choosing the matrix elements from a fixed probability distribution. What probability distribution? That's free. So there's not a natural choice, there's not a canonical choice. But if we impose this condition, now there's going to be a natural choice. Why are we doing the algebra like this? Notice that both of these terms have an A12. So we're putting the two terms with an A12 together, and then we divide by A12. And then we'll divide this by A22 minus A11. And that's how we get something like this. So that's where the A22 minus A11 on the outside is from over here. Let me just make sure the camera's going far enough so that Eliza can see. All right, so now we look at this. So we want these two sides to be equal. So I know some of you haven't taken any classes on differential equations, and now we have a differential equation where we have three variables that are being simultaneously differentiated. But this somewhat helps us. Notice on this side, what's the only variable at play? A12. What's the only variables at play over here? So function only of A11, A22. Function only of A12. So I want a function of A12 to equal a function of a11 and a22? What's the only way that can happen? So what does the value of this side have to be?
A function of p of the density of a12.
So it's going to, I mean, so this side is a function only of a12.
It doesn't have to be a constant.
It has to be a constant. If this had any dependence on a12, it's always got to equal this. We'll keep a11 and a22 fixed and vary a12. If this function varied, then I could violate the equality. The only way this can hold is if each side has to be a constant. Okay? That's the nicest function we could have. Now, it doesn't have to be the 0 constant. It could be 5, it could be -3. It's some number c. So the question is, what's the best way to write it? I think the best way to write it is -c. Yes. So we will write the constant as -c. Okay? So now we want to solve this. So we get, p12 prime of a12 is equal to -c a12 p12 a12. Or if you want, let's convert this to something that's a little bit friendlier. We want y prime of x equals -c x y of x. So any thoughts on what function might work?
Yes.
Okay, so what do you want to try? You want to try y of x equals what?
E3 something, but like I'm not sure what this is.
Okay, so let's put in an ax. And then y prime of x would be a e to the ax. And we've got an extra x over here. So unfortunately, e to the ax doesn't work.
X squared.
Let's try x squared. And then we'll get y prime is ax e to the ax. And if we want that to equal -c x e to the ax squared, what should we do? Oh, well, that works. What we do is we just take a to equal -c. So we get e to the -c x squared. Is this the most general solution? So, again, if you've never taken differential equations before, this is a quick introduction to differential equations. So I know that sometimes they put it in Calc 2, but I know a lot of you have done stuff like that in high school, so you may not have seen it.
Well, you still need that it integrates to 1, right?
Well, we have that because it's a probability distribution. Good. So we will be using that in a moment. But right now the question I'm asking is, we have y prime of x equals -cx y of x. And we said that y of x equals e to the -cx squared works. Does anything else work? Is there any other function that solves this equation? So the hint is, this is linear. What could I do to y of x and keep it as a solution?
0. Y of x is always 0.
Well, I could do that, but I wouldn't want to do that. So it is a nice solution. But so if this works, what else would work? What close cousin of this should work?
Plus c.
I'm sorry?
Plus.
Well, so let's see. So if I try plus c, well, let's not use c because we've already got a
Plus d.
plus d. I know, see, d, you almost think of derivatives. We can do a capital A.
Wow, it's a matrix.
Oh, you're right. That is a matrix right now. That's a bad notation. How about gamma? Because gamma is the third letter of the Greek alphabet, and that goes with C. So now if I take y prime of x, I will get negative cx e to the negative cx squared. But this is not going to be equal to negative cx y of x, which is e to the negative cx squared plus gamma.
What if you multiply that by gamma?
So if we multiply by gamma, then we're fine. So if we multiply by gamma, we're fine, because we then multiply this side by gamma, and we multiply this side by gamma. So this is the most general solution. Okay?
Or can you do like a linear combination of those?
Well, we only have, it should be a one-dimensional space of solutions. It's a first-order differential equation. We have one free parameter. The free parameter is gamma. C is actually determined. We don't necessarily know what the value of C is yet, but we know that there's some value of C. Now we use the observation that this is a probability distribution. So it has to integrate to 1. So we need the integral from minus infinity to infinity of y of x dx. This has to be 1. So this is now the integral from minus infinity to infinity of gamma e to the negative cx squared dx. So there's a couple of ways to do this. One is we can change variables, let x be square root of c times x, if we happen to remember what is the integral of e to the negative x squared. The other is we can write this as a normal distribution, and then just note what the integral of a normal distribution is. So this is the same as gamma, integral from minus infinity to infinity, e to the negative x squared over 2 sigma squared dx, 1 over square root of 2 pi sigma squared, and we'll have a square root of 2 pi sigma squared. And now, what does this integral equal? 1. So this is just going to be gamma times the square root of 2 pi sigma squared. Well, what's sigma squared? Well, negative, so c has to equal 1 over 2 sigma squared, with c equals 1 over 2 sigma squared. So 2 sigma squared is equal to 1 over c. So this should be gamma times the square root of, 2 sigma squared is 1 over c. So this should be, I think, pi over c equals 1. And now we can solve for gamma. So that should tell us, I believe, that gamma is equal to the square root of c divided by pi. I may have made a small error, I don't care. The main point is, once we know it integrates to 1, just do your favorite proof. If you remember what the integral of e to the negative x squared is, just change variables. Let u equal square root of c times x.
So is there a geometric interpretation for that? Because if it's equal to, it's a function of the variance of the distribution you're drawing it from.
Oh, in terms of this equation?
That term over there.
Okay.
The second term.
The second term?
Yeah.
This term over here?
No, this one.
This one? Okay.
And that's equal to negative c, which
Right.
is a function of the variance of your distribution. I'm wondering if that's...
Oh, I see what you're saying. I think. I guess the way I try to look at it at this level, where you're saying the derivative of the density is basically proportional to the density, and the constant of proportionality is a function of where you are. And so what density has that kind of behavior? And it turns out to be the Gaussian.
And so then c is your scaling factor, which makes
So C is some kind of scaling factor.
And then it makes sense it's related to the variance.
Yes.
Right.
Okay. So we've now handled the first term over here. We now have this term left. So any thoughts as to how we handle this?
Will you reference your notes?
I can reference my notes. It's in the book, but these are the things you've read. Or you can look at it now, and how would you want to attack this? This has to be a constant. This has to have no dependence on A11 and A22 at the end of the day. Right?
So can you say that each of those terms has to be constant?
So what if each term is constant? Well, if each term is constant, we've still got an A22 minus an A11.
So the difference must be constant? No, still.
Well, their difference, we know their difference has to be, we can multiply through, and it would be, the negatives cancel, we would get C times A22 minus A11 over 2.
Oh,
But we can maybe move things around. So we could get 1 over P of A11 dP11 over dA11 minus 1 over P22 A22 dP22 over dA22. And now this is equal to that constant, so we divide by 2, so we'll get a C halves, and we'll get an A22 minus an A11. So what should we do now? How should we group things? So what's making this hard is we have things mixed together. What made this so nice is we saw this depends only on A12, this depends only on A11 and A22. So the only way that this can hold is that this part here has no A12 dependence. It's got to be constant. So here we have things mixed up. How can we unmix things? Which things should we put together?
should divide by A22 minus A11.
Well, so we divide by that, we were returning back to where we were, right? And this was hard for us to study. So the problem here is things are mixed. I want to separate things. I want to collect all the A11s together and all the A22s together. So look, I've got a lot of A11s here, and I've got an A11 here. Why don't we put them all on the same side? And why don't we put all the A22s on the same side? And so if we do that, we get 1 over P of A11 dP11 over dA11. And now we have a minus, so that becomes a plus C halves A11. And then I move this over to the other side, and I'll have 1 over P22 A22 dP22 dA22 plus C halves A22. Okay, so it's very similar to solving linear equations from all these years ago. You have 3x plus 7 equals 4x minus 9. Put all the x's on one side, put all the constants on the other side, and now you can solve for x. I put all the A11s on one side, I put all the A22s on one side. What do we know about this now? And what do we know about this? They both must be constant. This is a function only of A11, a function only of A22. So they must both be constants. So now we have to decide, what do we want to call that constant? And so let me see what I'm choosing to call the constant this time.
You called it C.
I called it capital D, I think.
Yeah.
Okay. So each constant, say, I called it C times D. Oh, that was a smart thing to do. That's smart. No, notation is good. So why do I want to call it a C times D? We already know we have a constant C from a lot of the stuff over here. We've got a C involved over here. D is basically how things are being rescaled from that. And so now we want to solve these differential equations. Well, this is extremely similar to this one. All that we do is a search and replace from 1, 1 to 2, 2. So if we can just solve one of them, we have the other one. So it tells us that A11 and A22 will have the same density. And it may be slightly different than the density of the first. So we should have just enough time to finish. So now we've got, let's let y of x be p11 of x, just to make the notation friendlier. So now we get y prime of x, and we're dividing by y of x. And then we're adding c halves of x. And this is supposed to equal c times d. All right, so y prime of x is equal to cd minus c halves x times y of x. All right, so thoughts as to how we would solve this? It looks similar to the last one, but we've got this extra CD now. So this, I want to make sure, because this looks a little bit different than what I was expecting to get. Nope. Okay, it is. All right, this is what we have. So before we tried, e to the ax.
Yeah.
But now, because we have something more involved, when we had an x squared, we got an x coming down. Maybe we want something like cd minus c halves x squared. Because now when I take the derivative of this, that will come down. Well, actually, we don't want the a then. We're going to want, I think, a half. So when we take the derivative, the 2 will cancel with the half. When we take the derivative on the inside, we're also going to get a 2 cd minus c halves x times c halves. So I'll want, I think, a 2 over c.
Yeah.
And then we have a negative sign, so we want a negative. So it should be e, I think, to the negative 1 over c times this. And so now let's take the derivative. So y prime of x will be, take the derivative of this, so I'll get y of x back. And now I take the derivative of this whole piece, so I'll get negative 1 over c, cd minus c halves x. Now the derivative of this will be negative c halves. Oh, and I had a 2 that came down. So this all cancels, and it solves it. So we now get that y prime of x is equal to e to the negative 1 over c cd minus c halves x squared. So it's similar to the Gaussian we had before. Now what's nice here is the c's cancel, and you'll get it basically an x squared over 2, looking like a standard normal. Now the problem is we have this extra d. So what we want to do now is, we're running out of time, is basically we just translate the variable x. And by translating the variable x, we can get rid of the shift here and just adjust it so it has mean 0. So just changing the things. And so then what you'll see is that we had a slightly different variance of the main diagonal versus the off diagonal. The actual calculations here are somewhat interesting, but to me, the big picture ideas that I want you to get from this is we had a belief that it was reasonable to model a situation. Oops, I guess it's a little bit off focus. A belief where it was reasonable to model a situation where the probability of A and an infinitesimal tweak should be the same. And so the only way they can be the same is when we expand out the tweak, the first order term must vanish. What must be true of the second order term? It must also be 0. But then it gets more and more involved to calculate that. We can just look at the first order term and say the only way this can happen is the first order term must vanish. And that gave us a massive equation to solve. It was a differential equation involving 3 variables. In general, this is going to be very challenging to solve, but we were able to isolate things extremely nicely. And by arranging the algebra, we were able to say this part here only depends on A12, the other part depends only on A11 and A12. So we could solve this part first. Then we had the second part, and by playing algebra games again, we could get all the A11 dependence on one side, all the A22 dependence on the other side. The only way they can be equal is if they're both constant. And then we get another differential equation to solve. And fortunately, all the differential equations we need to be solving turn out to be Gaussians. And so for the next class, we'll now start looking at the consequences of this, and what does it mean to have the probability distribution coming from Gaussians. We're going to get a nice formula for the probability density of the eigenvalues of an n by n matrix. So I should probably at least write the word on the board at least once. GOE, Gaussian, orthogonal, ensemble. So the word ensemble is basically like a set of matrices. The Gaussian means that the entries are coming from the Gaussian, and the orthogonal means that the probability is supposed to be unchanged under orthogonal changes of the variables.
Yeah.
Okay. Good place to end.